discussing about asymptotes. I hope you can see my screen. Are you able to see my whiteboard? Yes. Meshach, are you able to see my screen?
Yes, I can see.
Okay, good. So limits and continuity. So we start by defining continuity at a point. So definition. So let's say we are real number. On the x-axis. So a function or the function f of x is said to be continuous at C if one, f of C is defined, and then to limit as x approaches C of f of x exists. And number 3, limit as x approaches C of f of x equals to f of C. Or had we discussed this to continue to in the previous class?
Don't think so.
Did we discuss continuity in the previous class?
Previous one was method separation.
It was an assignment.
No, we said we'd continue from there.
Okay, fine, good. Yeah. So those are the three tests for continuity. So one, for a function f of x to be continuous at a point C, f of C is defined.
Continuous.
And then limit as x approaches C of f of x exists. A limit of f of x as x approaches C is the same as f of C. Then the function f of x is right continuous at C, or we say continuous from the right, if limit of f of x as x approaches C from the right is the same as f of C. And then the function f of x is left continuous at this point C, or continuous from the left if the limit of the function as x approaches c from the left is the same as f of c. So please note that when you write c, then you write on top of c plus, we don't mean that now is plus c and this one is minus c. So plus simply means from the right-hand side, minus means from the left-hand side. But c remains to be a c the way it is defined in the problem. So I will draw a sketch to illustrate what we mean by these terms: continuous at C, right continuous at C, and left continuous at C. So if I have this as my x-axis, and then say this is my y-axis, so let this be point B. Let this be point A. And let's have a point C given at this point. So this is a graph of a function y equals to f of x. So you see from this direction, the function is continuous at A, but then from the right-hand side. So we say f is continuous or f has f is right continuous at x equals to A. And then at this point C, you see that if you approach the curve from the left-hand side at point C, you also have the same value as you approach the same point, say, from the right-hand side on the curve. And so we say that f is continuous or two-sided continuous at x equals to C. Because as you approach the curve at the point, say, from either direction, left-hand side and right-hand side, you will actually arrive at this point and get the same value. And then this point B, the function f is left continuous at x equals to B. So it means that you arrive at this value on the curve for the function y equals to f of x from the left-hand side, moving along the curve y equals to f of x. So that's why we can simply say at this point here, A, we have continuity from the right. And then at point C, two-sided continuity. And then at this point, we have continuity from the left. So a function which is not continuous at a point C is said to be discontinuous at the point C. So note that a function which is not continuous at x equals to c is said to be discontinuous at c, or simply have a discontinuity at c. Hello, Marim. Hello. Hello. So to test for continuity at a point, we check for the following. One, we check that the function f is defined at the point C and then number two, we check that the limit of the function at C exists. And lastly, three, we check that f of C is the same as limit as x approaches C of f of x. So if any one of these three conditions is not satisfied, then the function is said to be discontinuous at the point C. So for example, discuss or check the continuity of this function f of x equals x for x less than 1, 3 for x between 1 and 3, and x for x greater than 3. So what this problem actually is looking for is to check whether this function, so there's this point 1, and then there's this point 3. So we are interested in checking whether the function is continuous at x equals to 1 and x equals to 3. So there are 2 points of interest. So let's start with the first case, or case 1, x equals to 1. So there are only 3 things we have to do. We have to check the value of the function, whether it is defined at x equals to 1. And then number 2, find the limit of the function as x approaches 1. And then 3, see whether the two are the same. If all the 3 conditions are satisfied, then we conclude that the function is continuous at x equals to 1. So what is f of 1? And I hope you remember when you were discussing about different types of functions, this is an example of a piecewise defined function. So this f of x is defined by 3 different formulas. We have formula 1, we have formula 2, and we have formula 3. So according to the given conditions, if you want to find the value of the function at x equals to 1, which of the 3 formulas do you use as per the conditions specified? Which formula will give us f of 1? Remember, this is how the function is defined. F of x will be x for all values of x strictly less than 1. So that's when you use formula 1 as x. And then f of x will be 3 for any value of x between 1 and 3, 1 and 3 inclusive. And then the other way of defining f is x when x is strictly greater than 3. So for x equals to 1, which of the 3 formulas will be applied?
The second one.
The second one, because the second one is what is telling us that it allows us to evaluate the value of the function when x is allowed to be 1. So what would be the value of f of 1? If f of x equals to 3, what is f of 1?
3.
3. So f of 1 is 3. So this is well defined. Then limit as x approaches 1 of f of x. So remember here you are going to do it in 2 ways. You are going first to find the left-hand limit and then find the right-hand limit. And if the 2 limits will be the same, then you conclude that the limit as x approaches 1 of f of x exists. So what will be the left-hand limit? So limit as x approaches 1 from the left of f of x will be the same as limit as x approaches 1. Now, which function? By the way, if you are, once you have split this real line into these 3 portions, which function specify the interval from -infinity to 1 of these 3?
The first one.
Which function will be from -infinity to 1?
The first one.
The first one, x. And then from 1 to 3?
The second one.
Second one. And then from 3 to infinity?
The third one.
Third one. So which is now, third one is x. So when you say limit of f of x as x approaches 1 from the left, it means that now you are from this side. So you're approaching 1, but from this side. So which means that the f of x will be x. So we'll have x. And what will be the limit as x approaches 1 of x? What the value of that limit? What will be the value of that limit?
One.
Which just 1. So just direct substitution should give you the answer, correct? 1. And then let's calculate the right-hand limit. So we'll have limit of f of x as x approaches 1 from the right. So this will be limit as x approaches 1. Now from the right to approach 1 means that you are moving from this side. You are going towards 1, but then moving from the right-hand side. So which function do we use? As you approach 1 from the right, f of x is? F of x will be? Remember when you are splitting this, these are the values of f of x in these intervals. These are the values of f of x.
Will be 3.
So which f of x will be used when we are approaching 1 from the right-hand side? Okay? The value of f of x, obey?
3.
3. So limit as x approaches 1 of 3. So what will be the answer? Or the value of the limit? Limit as x approaches 1 of 3.
3.
3. Now, we see that limit of f of x as x approaches 1 from left is 1, which is not the same as limit as x approaches 1 from the right of f of x, which is 3. So what is the verdict? Does the limit of the function at x equals to 1 exist or it doesn't exist? When two one-sided limits exist, but they are different, they have different values. What is the conclusion? Does the limit exist at that point or it doesn't exist?
Does not exist.
Does not exist. So the limit as x approaches 1 of f of x does not exist. And actually the reason is because one-sided limits exists but have different values. So what is the verdict? If the limit doesn't exist, is the function continuous at x equals to 1?
No.
No. So since limit of f of x as x approaches 1 doesn't exist, the function f of x is not continuous at x equals to 1. And actually, as we shall see later on, when you're discussing different types of discontinuity, this type of discontinuity is called jump discontinuity. So jump discontinuity is whereby one-sided limits exist, but they are different values. So the limit of the function doesn't exist at that given point. Good. And then lastly, case 2, let's discuss the continuity at x equals to 3. So what is the value of the function at x equals to 3?
3.
3, because remember, the function was giving us 3 whenever x is between 1 and 3, both 1 and 3 inclusive. So when you want to calculate value of the function at exactly x equals to 3, we must use the middle branch. So this is 3. So f of 3 is well defined. Now, let's get the limit at x as x approaches 3. So limit of f of x as x approaches 3. Now, because the function is piecewise defined, you have to compute the two-sided limits and check whether they give you the same value for you now to conclude the value of the limit at as x approaches 3. the left-hand limit will be x approaching 3 from the left of f of x approaching 3 of f of x. Now, which of the three functions we'll use for computing the limit as we approach 3 from the left-hand side at this point?
The second one.
Second one, because now remember, we want to approach at x equals to 3, but you're moving from the from the left-hand side. So this is how we are going to approach the point x equals to 3. And this is a function of the branch that we are going to use. So this will be the same as limit as x approaches 3 of 3. And what will be the value?
3.
Limit of a constant is just a constant, 3, correct. Then limit as x approaches 3 from the right is the same as limit as x approaches 3. Now you go back to your sketch here. Then we want to approach the point 3, but then from that direction. So which f of x do we use? Which value of f of x?
The third one.
Third one. So x. So as x approaches 3, f of x equals to x becomes?
Three.
3. So since the left-hand side limit is the same as 3, which is the same as right-hand side limit, then limit of f of x as x approaches 3 is the same as 3. So i.e. limit exists. So the limit of the function f of x as x approaches 3 exists and the value is 3. And we also saw that the value of the function at x equals to 3 is 3. So since f of 3 is 3, which is the same as limit as x approaches 3 of f of x, what will be the verdict about that point?
It is continuous.
The function f of x is continuous about the point, or at the point x equals to 3. So we can briefly discuss the different types of discontinuities before we give more examples. So types of discontinuities. So the first one is what we call removable discontinuity. So this occurs when the limit of the function at x equals to c exists, and f of c is defined, but f of c is not the same as limit as x approaches c of f of x. So for example, let me draw a sketch. So they have this function here. Say this is 5, and I have this is 10. Then this is 2. But if this is the structure of our sketch, what is the f of 2 at this for this function?
10.
10, correct. Where we have a closed hole. And what is limit as x approaches 2 of f of x?
5.
5. So we say f of 2 is 10 and limit as x approaches 2 of the function f of x is 5. So this is y equals to f of x. So the value of the limit and the value of the function at point 2 are not equal. So that's a structure that shows an example of a removable discontinuity. But the beauty with this type of discontinuity is that you can always redefine the function to make it continuous. So what we'll do, we retain the same function, but now instead of defining f of 2 at 10, we reduce it to p at this point so that this hole is closed. So we bring this value of the function at 2 to this point here, and then for these 2, this is 5, and this is where we had 10. So this is 0. So this remains to be y equals to f of x. So in this case, we say that this is removable discontinuity at x equals to 2. Then here, function redefined at x equals to 2 to make it continuous. So that's the beauty with this type of discontinuity that we call removable, that the limit of the function exists at the point x equals to c, and the value of the function at the point equals c also exists. But the only condition which is not satisfied on the definition of continuity is that the value of the limit and the value of the function at the specified point are not equal. So what you normally do, you retain your limit value the way it is, and then redefine the value of the function at that same point. So once you have that one, you make the function continuous. Like you may be asked, what is the value of k that makes f of x continuous at x equals to 2, assuming we have f of x defined as x squared minus 4 over x minus 2 for x not equals to 2, and k for x equals to 2. So if you remember the definition we gave for limit at a point x equals to c or x equals to a, is that we are interested in saying the value of the function as we get closer and closer to the point x equals to c, not necessarily at the point c itself, but how the function behave as we get closer or near and near the point c. So here, f at 2 in this function will be given by
K.
k, because we have already been from the definition of the function that the function f of x equals to k for x equals to 2. So if I want to find f at 2, then I'll use this value or this definition. So this is k. So this one is defined. Then next we get the limit as x approaches 2 of f of x, and this will be the same as limit as x approaches 2. Now I use this other function, this other branch of the function, x squared minus 4 divided by x minus 2. So which limit method do we use to evaluate the present limit? Which technique do you apply?
Factorization.
Factorization. So we can write this one as limit as x approaches 2 of x minus 2, x plus 2 divided by x minus 2. And by doing so, this bracket and this bracket cancels out, so that we'll have a limit as x approaches 2 of x plus 2. And what will be the value here? What will be the value?
4.
4, just 2 plus 2. So we have the limit of the function f of x is given by 4. And then now, remember, we are looking for the condition which makes this function continuous at x equals to 2. So for the function to be continuous at x equals to 2, there are 3 things to be satisfied. F of 2 should be defined. Limit as x approaches 2 for the f of x should exist. And then 3, the value of the limit as x approaches 2 should be the same as the value of the function at x equals to 2. So then you just say for f of x to be continuous, at x equals to 2, then f of 2 the same as limit as x approaches 2 of f of x. And we have found f of 2 is given by k, and limit as x approaches 2 of f of x is 4. So therefore, k must be 4 for the function to be continuous at x equals to 2. So another question is the function g of x given by x squared minus 25 over x minus 5 for x not equals to 5, and here for x equals to 5, continuous. Is a function given by g of x defined piecewisely as this, continuous at x equals to 5. So the answer depends on whether all the three properties of continuity at x equals to 5 are satisfied. So the first thing, what is the value of f at 5?
15.
15. So this is defined. So that's first property is okay. And then let's get limit as x approaches 5 of f of x, which is the same as limit as x approaches 5 of x squared minus 25 over x minus 5. So can you compute that limit? So can you compute the value of the limit?
10.
10. By which method have you applied?
Factorization.
Factorization. So x approaching 5, x minus 5, x plus 5, and then divided by x minus 5. So x minus 5 cancels out. X minus 5, x minus 5. So that we'll have limit as x approaches 5 of x plus 5. And then by direct substitution, just have 5 plus 5, which is 10. So we have that as our limit. So then now, so this first condition, second condition, now third condition is f of 5 equals to limit of f of x as x approaches 5.
No.
Are they the same?
No.
They aren't. So since limit as x approaches 5 of f of x, which is 10, is not the same as the value of the function at 5, then the function, actually this, we were to use, just check this one, change this one to g because that's the definition of the function, not f. So this is g of x, g of 5. So g of 5, then limit of g of x. These are g functions. So just to be consistent with the name of the function given. So limit of g of x, this is g of 5. Then the function g of x is not continuous at x equals to 5. But this discontinuity can actually be redefined to make it continuous. So what should we do? What should we redefine for this to be continuous?
We should substitute the value of g of x at 5. Instead of 15, we have 10.
Yes. So if we redefine g at 5 to be 10, then g of x becomes continuous. So this is an example of removable discontinuity. And remember, what you can modify is the value of the function at the point x equals to c. But the limit, you don't interfere with it. So you simply now change the value of the function as defined at the point c to be the same as the value of the limit calculated. Then the function will be continuous. Then the other worst discontinuity where you can't do the redefinition of the function to make it continuous is what we call jump discontinuity. So this is B. Jump discontinuity. So this occurs if the one-sided limits, say limits of f of x as x approaches c from the left, and the limit of the function f of x as x approaches c from the right exists, but they are not equal. So we can actually give an example graphically. If I have this as my y-axis, this is my x-axis, this is 0. If I have a function which is defined as so there is 0.2, and let this be 10, and let this be, say, 6. If this is how the graph is drawn, are you able to tell me the value of f at 2? The way this sketch is given, what is the value of f at 2?
6.
F at 2 is
6.
6. Remember, we just pick that which is actually the value where we have the closed hole. That's what give us the value at the exact point. And what is limit of f of x as x approaches 2 from the left?
6.
What be?
6.
Remember, in mathematics, our left is left. It's not like biology. So what you are saying as left is actually exactly what you are referring to as left. It's not biology where left is right and right is left. It's the way you sit. So if I call this branch A, this one branch B, the limit as x approaches 2 from the left of f of x, we'll use A or B.
A.
We use A. So what is the value of the function as we get closer and closer to point x equals to 2 along that curve A?
6.
6. And what is the value of the limit as x approaches 2 from the right of f of x?
Please don't.
Will be?
Ten.
10. So remember, we'll be moving along the branch B. So, and then the value of the function is here given as 10. So this will be 10. So clearly you see here, limit as x approaches 2 from the left of f of x is 6, which is not the same as limit as x approaches 2 from the right of f of x, which is 10. So because the two limits exist but they are different, then the limit of the function does not exist, and therefore this function describes what we call a jump discontinuity. Now for jump discontinuity, because the problem comes with limits, we can't remodify them to be continuous. They remain to be, we can't redefine them to be continuous. The discontinuity remains the way it is. We can't do redefinition for the function to be continuous. And then, so just maybe you can just make that. Let me give another sketch probably before we make that conclusion. If I have this as my y-axis, this is my x-axis, and I have another, say I have, let's say this point 3, and I have this other branch, and I have, so let this be 10, let this be 8, and let this say be 6. So let's have that sketch. And I would like you to tell me the value of this function at 3. What is f at 3? 10, correct? And what is the limit of f of x as x approaches 3 from the left?
Six.
6. And limit as x approaches 3 from the right of f of x will be?
8.
8. So this is also another example for a jump discontinuity where the two one-sided limits exist, but they are different. So the function is discontinuous at x equals to 3. So unlike the removable case, we cannot make f of x continuous by redefining f of c. Because already the limit doesn't exist, then there is nothing we can do that we can change the value of we can change so that all the properties of or all the conditions of continuity are satisfied.
Hello. Ati? Kana tuma. Nimeona total imekuja 610.
So there's what we call the infinite.
Ati? Sawa.
Discontinuity. So this occurs when the one-sided limits are when one of the one-sided limits is infinity or even both of them. So when one of the one-sided limits or all the one-sided limits is infinity, then we have what we call infinite discontinuity. For example, I can make some sketches here. This point 2, and we have a function f of x with this property. So this is an example of a sketch of a function which has an infinite discontinuity because both the one-sided limits will actually be giving us infinity. And then another example of a sketch of a function whose discontinuity of infinite case, we can have this still at 2, this x 0, we have this graph. So this is another example of a sketch of a function which has an infinite discontinuity at x equals to 2. And we can also give another example here. Okay, what if I call this case A? This is our case A. This is our case B, and this is our case C. What makes B to be called or to have an infinite discontinuity? Which one-sided limit is having infinity as this solution at x equals to 2?
The right-handed.
Right hand or left hand?
Right.
Right hand, yes. So the right hand limit in this case 2 is what is giving us an infinity. So limit as x approaches 2 of f
Yeah,
of
kwanza
x
Ishaka, chill.
from the right is what is
Hello.
infinity.
Hey.
So I give you 5 minutes break, then we can come back to discuss the limits at infinity.
Your back pain? Breathing in just hurt. Your back pain or you have carrying out the cold again? My back is